This is the Launch Explore Discuss for Unit 1, Lesson 2, Flipping Ferraris. We're going to go right into the launch here. When people first learn to drive, they're often told that the faster they're driving, the longer it will take to stop. So when you're driving on the freeway, you should leave more space between your car and the car in front of you than when you're driving slowly through a neighborhood. Have you ever wondered about the relationship between how fast you're driving and how far you travel before you stop after hitting the brakes? Well, think about it for a minute. What factors do you think might make a difference in how far a car travels after hitting the brakes? So you could have a lot of answers here, but if you think about it, factors that makes a difference, you might think of reaction time, how quickly can you hit the brakes. You might also think of the condition of the road, whether it's wet or dry, what kind of tires, what kind of brake pads the car has. So there's a lot of things that could go into the answer for number one. You can put down just about anything you can think of. So it says there's been actually a lot of experimental work done, mostly by police departments and insurance companies, to be able to mathematically model the relationship between the speed of a car and the braking distance. That's how far the car goes until it stops after the driver hits the brakes. So imagine your dream car, okay, and then they list here a Ferrari 550 Maranello, and that is pictured right here. Just got that off the internet. Pretty sweet. Definitely not a family car. And let's see. Experiments have shown that on smooth, dry roads, the relationship between the braking distance and the speed is given by, and then we have a function, d of s equals 0.03 s squared. So d is the distance, and s is the speed. How many feet should you leave between you and the car in front of you if you are driving the Ferrari 55 miles an hour? Well, that's a simple substitution. D of 55. So 0.03 times 55 squared. And looking that number up, it is 90.75 feet. What distance should you keep between you and the car in front of you if you're driving 100 miles an hour? 100 miles an hour, D of 100, 0.03 times 100 squared, that goes all the way up to 300 feet. That's about the length of a football field. If an average car is about 16 feet long, how many car lengths should you have between you and the car in front of you if you're driving 100 miles an hour? Well, simple division will do it. It's 300 divided by 16, and the answer is approximately 19 car lengths. It makes sense to a lot of people that if the car is moving at some speed and then goes twice as fast, the braking distance will be twice as far. Is that true? And you can explain. Well, we just saw what 100 miles an hour would take. It would take 300 feet. But what about the stopping distance at 50 miles an hour? Half of that. So D of 50 is actually 75 feet. So if you look at the ratio of those two numbers, 300 versus 75, and that's 75 feet, it's about 4-to-1. So if you double, then you quadruple. And this is because of the square. Interestingly enough, the same works with wind resistance or air resistance. So you really do have to watch it when you start going fast. Graph the relationship. Okay, so I put the relationship into Desmos, and it looks something like this. They would like us to list the domain. So the domain actually is going to just start at 0 because these are numbers that you could have on your speedometer. So 0 to 217 is where this one would stop. And if you plug 217 in to the calculator, you get 1412, almost 1413 feet. It's increasing throughout that domain. The minimum is 0, the maximum is the corner 217, 1413. So let's get all that down over here. Yeah. So domain would go from 0 to 217 inclusive. That means the endpoints are included. The range would go from 0 to 1413. That's inclusive. D of S increases on the domain. And 0, 0 minimum, and 217, 1413 is the maximum. So now, what if, part number 5, what if the driver was cruising along and suddenly hits the brakes to stop because she saw a cat in the road? She skidded to a stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car, so she knew that her braking distance was 31 feet. How fast was she going when she hit the brakes? Well, there's 2 ways we could do this. One is we could substitute into the function and then solve, or we could solve the function ahead of time and then substitute. So I'm going to do the first way on A, and I'll do the second way on B. So the first way would be if you had 31 is the function outcome, and it equals 0.03 s squared. So to solve that, you would want to divide by 0.03. So divide here, and that would give you s squared. So whatever that is, s, I'm going to carry it over to the right here, s squared equals 31 over 0.03, and then we would take the square root. And s would turn out to be 32.15 miles per hour. So not too fast, right? Now, if we just take what we did and replace the 31 with a d, then we can actually make an s of d by saying that that's the square root of d divided by 0.03. And so if she's 15 feet away in this new problem, just take s of 15. So you take the square root of 15 divided by 0.03 in your calculator, and you will get 22.4 miles per hour. Now, part of the job of police officers is to, investigate traffic accidents to determine what caused the accident and which driver was at fault. So what they do is they measure the braking distance using skid marks and calculate speeds using mathematical relationships, just like the one we did here. Although they often use different formulas to account for various factors, such as road conditions. That means, was the pavement hot? Was the pavement wet? Things like that. Let's go back to the Ferrari on a smooth, dry road since we know the relationship. Create a table that shows the speed the car was traveling based upon the braking distance. Well, we've already calculated some things here. So if we just go braking and speed. Remember, we want to use the rule of 4 whenever we can, look at functions in different ways. You're not going any speed. You don't have to have any braking distance. You're going 50 miles an hour. You needed 75 feet. You're going 100 miles an hour. You need 300 feet. And if you're going 200 miles an hour, and I just previously calculated this, it's 1,200 feet. Okay, next, number 7, write an equation of the function s of d. Well, I kind of jumped the gun on that. I did that up here. My s of d, remember, was the square root of the distance divided by 0.03. Now, if we graph that function and describe its features, what we're going to get is something that looks kind of like this. Now, its domain will be from 0 to 1413. Its range will be from 0 to 217. And it does increase. Zero, 0 is the minimum. And 14, 13, 217 is the max. Look familiar? It should look familiar. That's a lot of the reversals of what we got for the other function. I'm going to need a cough drop today. Number 9. What do you notice about the graph of s of d compared to the graph of d of s? What is the relationship between the functions? Well, you kind of already know. These are inverses, right? They are inverses that reflect across y equals x. And I have a picture for you here to the right from Desmos, putting in both of those functions. And actually, what I did was go ahead and tick off the restriction on domain and range and just let it be everything so you can really see the reflection. Now, if it doesn't look like a perfect reflection, that's because my squares are not really squares. In other words, if you notice, this is a little bit off from being a square. So that distorts the view. But we do get this nice reflection. I did a little trick here to get the square root to display above and below the axis. I put in a negative, and that flipped it so that it would show me the bottom as well. But again, this is the big point here, is that inverses reflect over the line y equals x. Okay, so let's finish this thing off here. Consider the function d of s equals 0.03 s squared over the domain of all real numbers, not just the domain of this problem situation. Does the graph change from the graph of d of s in problem number 3? Yeah, then you get the entire parabola. You get the entire parabola. What's a parabola? From integrated 2, I remember it's this shape we get right here. So you get the whole thing, not just the right side. And then I did that little trick and I got this other parabola here laying on its side. 11, how does changing the domain of d of s change the graph of the inverse of d of s, And then, well, it looks like the graph. That's our graph. It looks like an entire parabola one way. So if I just sketch this out real quick, an entire parabola one way and an entire parabola the other way. That's not very good. But anyway, it's supposed to reflect across y equals x. Just look at my picture here. That's much, much better. Okay, and number 12, is the inverse of d of s a function? No. For every input, is there exactly one output? No. See, it fails what we call the vertical line test. Right there. There is an x value that has two distinct y values. So, no, not a function. What they're getting at, and what we're going to get to in a future lesson, is you got to restrict the domain so that the inverse becomes a function. All right? So that's coming soon. And that would actually create what we call a one-to-one function. And let's see, did I have a picture of that here? No, I didn't. But if you turn off the bottom part here, if you just take that away and you take this away, then both the function and its inverse are what we call one-to-one. That means for every x, there's only one y, and for every y, there's only one x. So in the future, right here, future thought will be one-to-one functions. And how we can restrict the domain to create those. Okay, so pretty good so far. I know this video is getting a little on the long side. The takeaways are very similar to what we've done in the past. I'll just mention them, don't necessarily want to write them. The graphs reflect over y equals x. Inverse operations reverse the order. Inputs and outputs are switched. The domain of f is the range of f inverse, and the range of f is the domain of f inverse, and all that vice versa stuff. And here's a word that we want to pick up on, invertible. One little last thing. An invertible function means that its inverse is a function. Invertible function, there's a space right there to write it. A function whose inverse is a function. Okay, well, we're going to go ahead and end right there. We'll see you next time.